One of the most important compounds in all of chemistry, both for theoretical and practical industrial reasons, is this compound benzene. Benzene has the chemical formula C6H6, and its perhaps most distinctive feature is that the 6 carbon atoms form a ring. And this is the structure that was famously decoded by August Kekule, apocryphally perhaps, him having fallen asleep and dreamed of a snake swallowing its tail, and that gave him the insight that the only way to explain the reactivity of benzene experimentally was if it were a ring. Now, this is one of the ways that we often denote benzene, and we have alternating single and double bonds. It turns out that in reality this is not the actual structure, because in the ring the electrons are delocalized in such a way that rather than having longer single bonds and shorter double bonds, all of the carbon-carbon bonds have identical lengths and all the bond angles are equivalent. So we end up with a structure that is essentially a perfect hexagon as far as the carbon atoms go. And all the carbon-hydrogen bonds, again, have identical lengths. To demonstrate this, and also because trying to draw the practically ubiquitous benzene ring with 12 atoms gets to be a lot to write, we often write it in a shorthand. And the shorthand that chemists use most often to denote benzene is to emphasize the ring structure. So we draw a 6-sided hexagonal ring, and then to remind us of the delocalization of electrons throughout the ring, we put a circle inside. So here we're using the organic chemist convention that whenever we draw a line, at the ends of the line we imagine that there are carbon atoms. So since there are 6 vertices, there must be 6 carbon atoms, and that we mentally fill in the number of hydrogen atoms that are necessary to account for the valence of carbon. So we have to remind ourselves that even if we draw it this way, that there are still 6 hydrogen atoms that's each attached to one of the carbon atoms, even though we haven't explicitly written that out. So let's look at the point group symmetry of this particular molecule. So one of the first things that we notice is, since it's a perfect hexagon, we can rotate it in a plane of the board around this particular axis. And one of the rotations that we have is if we go by 60 degrees, we see that we have a C6 rotation. So perhaps the most distinctive feature of benzene is the presence of this C6 symmetry element. By exactly the same sort of reasoning, if we go in the opposite, we always have E, we have C6. We have C6 to the -1 because we could just as well rotate in the clockwise direction, and again the molecule would look the same as it did before. Let's see what other rotations we have. Well, if I rotate by 120 degrees, so I start up here and rotate to there, I can rotate by 120 degrees and all the carbons will line up identically to their position before. All the hydrogen atoms will line up, so therefore we have a C3. So there's a C3 as well as a C6. And we realized that we could get this by doing 2 C6s in a row in this particular case. But using the same logic that we've used before, if I rotate by 120 degrees in the clockwise direction, that would give me C3 to the -1. Let's see, do we have any other higher rotation axes in the plane of the board? Yes, we have one more. So I'll try to denote this by green. And I can rotate the benzene molecule by 180 degrees, and that shows me that I have a C2 in this particular plane. So we have quite a few high-order rotation axes in the plane of the board, and our high-order rotation axis is going to be our C6. So right away, we know that that's going to be a key feature in naming the point group for this particular molecule. Let's see if we have any other important symmetry elements. Typically, after we found the high-order rotation axis, we want to start looking for other C2s, particularly those C2s, which are going to be perpendicular to the high order rotation axis. Well, let's see if we can find it. Well, we can find one that goes along here. So if I rotate around this, typically we call the 1 and 4 carbons. I have a C2, and we call this C2 prime because it's going through 4 atoms, it turns out, 2 carbons and 2 hydrogens. So this would be a C2 prime. We notice that we have a number of these C2 primes because we also have a C2 prime that goes here. And we also have a C2 prime that goes this way. So we see that we have 3 of these C2 primes. This would rotate us out of the plane of the board. And the actual axis is in the XY plane. We notice that if I hold up my dowel to demonstrate where the high order rotation axis is, we see that these 3 C2 primes are all normal. They're all perpendicular to the high order rotation axis, which tells us, if we found even one of them, it tells us that we must have some sort of a D group. So right away we know that we must have D6 something or other. So we at least have D6. We know it's a D group because we found at least one C2 perpendicular to the high order rotation axis. Well, let's see if are there any other C2s. We know from theory that there must be 3 more C2s that are perpendicular. There must be N C2s perpendicular to a CN axis if I have a DN group of some type. So let's see where those others would be. We'll redraw our benzene molecule to make things a little clearer here. And we'll also notice that to make things less cluttered when I'm drawing it, for the sake of clarity, I will often leave out the circle in the center of the benzene ring. For the time being, for this entire episode, we're talking about the symmetry of benzene and benzene derivatives, so even if I don't put that circle in there, keep in mind that that's what I'm representing. So let's see if we have any other C2s. Well, we can draw a C2 that goes along here, and we can rotate along it. And since this goes between, it doesn't actually go through any atoms at all, this is going to be a C2 double prime. So we have a C2 double prime rotation. We have one there, we have a second one that goes along this particular axis. So we found 2, and then last but not least we have a third which goes along here. So we've been able to find 3 C2 double primes for this particular point group. What else do we need to find? Well, we found all the C2s. We're really interested in the mirrors at this point because the mirrors will tell us whether we have, if we have a horizontal mirror, we'll have a D6H. If we have a dihedral mirror, we'll have a D6D group. And if we have no mirrors at all, we would have simply the point group D6, which exists, but we do not have a good example of it with benzene here. So let's draw our benzene one more time and see if we can find mirrors. Well, the simplest mirror to look for, and the one that we want to look for the most, is see if there is a mirror perpendicular to the high order rotation axis. And since our dowel is our z-axis, our high order rotation axis goes along the z-axis. If we have a mirror in the plane of the whiteboard, that would tell us that we have a horizontal mirror because it's perpendicular to the high order rotation axis. And we have such a mirror. So we do have a sigma h. So that tells me right away, even before I look for other symmetry elements, that we must have the point group D6H. So our classic example of D6H in geometry would be a perfect hexagon. Our chemical example of D6H is the compound benzene. Let's just look for a couple more of the important symmetry elements of benzene, just to see if we can find those. We have enough already to classify the molecule, but it's good to be able to see where these particular elements are. If I look relative to a center point, say to the center of the hexagon, and then I draw a line to each of the atoms. So for example, if I draw a line in this direction, I could draw a arrow that has exactly the same length in the opposite direction. and I would encounter another point of the molecule. Right now we're just doing the carbons, but we would be able to follow the same exact logic for the hydrogen atoms. If I draw a vector from the center to this particular carbon, I could just as well draw an equi-long vector in the opposite direction, which also reaches a carbon atom. And we'll do this one last time for the last carbon in this direction. I can draw an equal and opposite vector in the opposite direction, which reaches and comes up to a carbon atom. Because I can do this for any atom in the molecule, that tells me I have the special symmetry operation of inversion. So one of the important things about benzene is I can determine experimentally using our vibrational spectroscopy that it has a center of inversion. Now notice this is actually a useful way to prove that the initial structure that we had drawn for benzene is not correct. Since we know that a carbon-carbon single bond has a different length than a carbon-carbon double bond, if benzene really had that structure of alternating bonds, it would not form a perfect hexagon. Also, if we reference some central point, we would notice that that particular structure does not have a center of inversion. Since we can easily determine from benzene is a common chemical that we find in the laboratory, we can easily do vibrational spectroscopy upon it and determine beyond any doubt that it does have a center of inversion. So that's additional evidence that the structure we believe to be true for benzene actually is true. So that's center of inversion. Does it have any mirrors? Well, this also has lots of mirrors. We have mirrors that go up and down this way. So perpendicular to the plane of the board, we have mirrors here, here, and here. So those mirrors are vertical mirrors. So we have 3 vertical mirrors. Let me try to denote where the vertical mirror is going to be here. So here would be one of the vertical mirrors. We go along this line, the green line, and this would be a sigma V. And the reason why we call it a vertical mirror, we know it's not a horizontal mirror because it's not perpendicular. But the reason for giving a specific designation of vertical is that it goes through 4 atoms. So since it goes through the largest number of atoms, it's going to be the vertical mirror. And then we're going to see what a dihedral mirror looks like and show that it's different. So here we have another vertical mirror. Again, it goes through 4 atoms. And then we have a third sigma V. So we're able to find 3 sigma V's in benzene. What we want to find now are the dihedral mirrors. So these are the ones that are a little tricky. So let's kind of show where these are and why we name them the way we do. Well, I also have a mirror that will go between the atoms. Since it goes between the carbon atoms and between the hydrogen atoms, this is a perfectly good mirror plane. It's not a horizontal mirror because it's not perpendicular to the high order rotation axis. It's not normal to it. But it's not a vertical mirror because it goes through fewer atoms than do the vertical mirrors for this particular molecule. So we give the designation of a dihedral mirror. So this is sigma D. We can think of sigma D as just being a special case, a special kind of name for what is basically a vertical mirror. We have a dihedral mirror there, and then last but not least, along this particular axis, we have a plane that's going to be our sigma D. So we also have 3 dihedral mirrors for benzene. So now let's look at what happens when we make substitutions into the benzene molecule. So we take our benzene and we're going to make modifications to it. The first and easiest modification that we can make is to halogenate the benzene molecule. And halogen derivatives of benzene are of enormous importance industrially. So the first thing we want to do is make the mono substitution. So let's replace one of the hydrogens by chlorine. And just to make it look nice, I've put the chlorine atom at the top as I've drawn the molecule. All 6 positions of benzene are equivalent. So it would not matter which of the hydrogens are replaced with chlorine, we get the same molecule. So now we want to see what's happened to the symmetry operations of the molecule and see if we can classify the point group symmetry of this particular molecule. Well, if we do that, the first thing we want to look for is that C6. We know the C6 is the high order rotation axis for benzene, and right away we see that by mono substituting it, making the chlorobenzene, if I rotate the molecule by a C6, it would take chlorine into hydrogen, which isn't the same thing, so we no longer have a C6. If I tried to rotate by 120 degrees, it would take chlorine into hydrogen, so there's no C3. If I tried to rotate chlorine to here, it would take chlorine into hydrogen, so there's no C2s either. So, perpendicular to the plane of the board, the high order rotation axis is nothing more than the identity. So I've taken away a C2, C3s, and C6s. Well, let's see what symmetry operations do we have. Do we have any rotational axes of any interest? Well, we do have one. If we go along the axis of the chlorine through carbon, and then hydrogen would be down the other end, along this axis, we have a C2. So we do have a C2 as our high order rotation axis for this particular molecule. Do we have any other C2s? No, that's the only one we have. But we do have, in addition to the identity and the C2s, let's see what we have. We have the identity, we have a C2. We also have two mirrors. One mirror goes along this red line and is perpendicular to the plane of the board. That's a mirror plane. And we also have a mirror in the plane of the board. Now, notice the mirror in the plane of the board actually includes our C2. And in fact, this mirror plane also includes the C2. Because they include the axis and are not perpendicular to it, neither one of those two mirrors is a horizontal mirror. They're both going to be vertical mirrors. So again, we have the point group with the identity, a C2, and two vertical mirrors. And by now, we should be pretty good at recognizing that this is the point group C2V. So a monosubstituted benzene, if it's monosubstituted with a halogen, whether it's chlorine, fluorine, bromine, or iodine, is going to now belong to the point group C2V. It's chlorine, fluorine, bromine, or iodine is going to now belong to the point group C2V. We would now like to examine the di-substituted, the dihalogenated benzenes. So that's our remind ourselves of the structure of benzene here itself. And then we would recognize from organic chemistry that there are three distinct ways to dihalogenate a benzene molecule. So the first, we're going to use fluorine just to change it up a bit. So let's put the two fluorines right next to each other. So recall that this is the ortho difluorobenzene, or also the 1,2 difluorobenzene. So this is one of the ways of di-substituting benzene. So we want to see now what the high order rotation axis is and such. We notice that if we go along this particular axis, we no longer have a C6, a C3, or a C2. We don't have any interesting rotation axis along Z other than the identity. The only C2 we're going to have is going to go through here, so between the two fluorine atoms, but we will have a C2. Along this same line, we have a vertical mirror, and we also have a vertical mirror in the plane of the whiteboard. So that tells us that this particular di-substituted ortho difluorobenzene is going to have the point group C2V. So we see that going from a monosubstituted to a di-substituted benzene does not change the point group assignment, at least if the di-substitution is ortho. So next, we recall that the second way that we can di-substitute benzene is as follows. In this case, we'll use bromine just to vary up our halogens. So now we notice that there's a space in between. This type of di-substitution pattern we refer to as meta. So this is meta-dibromobenzene, or we can refer to it as 1,3-dibromobenzene. And we're interested in the point group symmetry of this particular compound. In the plane of the board, we have no interesting symmetries other than the identity. our high order rotation axis will go through this particular line, and this again gives us a C2. It takes us out of the plane of the board. Along this same line, we're going to have a vertical mirror. And again, we have a vertical mirror in the plane of the board. We're going to notice that for almost all the compounds that we're doing with benzene in this particular episode, that almost invariably there's going to be a mirror plane in the plane of the board because the benzene ring itself is planar. So since we have the identity C2 and two vertical mirrors, we have, perhaps boringly, again, another example of C2V. So it seems that the style of dye substitution doesn't, at least far so yet, seem to make a difference, because if we have an ortho dye substitution or a meta dye substitution, we still get the same point group that we had with a mono substitution, C2V. But when we get to the third and final type of dye substitution, we will actually see something interesting happen in that we get a different point group. So let's take a look at that. Arrange our unsubstituted bromine at first, and we're going to dye substitute it with iodine. In this particular case, we now have the para substitution. So this is para diiodobenzene, or the 1,4-diiodobenzene. Now we actually have something interesting happening in the plane of the board, because if I do a C rotation along this z-axis, I notice that if I go by 180 degrees, it will take iodine into iodine, carbon into carbon, carbon into carbon, hydrogen, hydrogen, such. It will look invariant. It will look the same if I do a C2 in the plane of the board. So it tells me that I do have a high order rotation axis coming out of the plane of the board. And one of the ways that we can refer to this is not only as C2, but since the axis is the z-axis, sometimes we refer to this as C2z, just to remind us where the axis is for this. Do we have any other rotational axes? Well, if I go halfway through the molecule like this, I notice that if I rotate it, it will take iodine to iodine, carbon to carbon. So I do have a C2 in this particular plane. I also have a C2 going through the iodines. So kind of put it up here, coming out the bottom. So there's also a C2 axis this way. And I notice that this particular C2 is perpendicular to the C2 that's coming out of the plane of the board, the z-axis C2. So we notice, and then this one along the x-axis is also perpendicular. So I notice that the C2 on the x-axis is perpendicular to the C2z, and I have a C2y that's perpendicular to C2z. Since I have two C2s that are perpendicular to a C2, that tells me that I have a D group now. So I actually have D2 something, and the only thing that we're left to do is to look for a distinguishing mirror plane, if one exists. And I notice that I still have the plane in the plane of the board, and this mirror is perpendicular to the C2z high order rotation axis. There are other mirrors in this molecule also, but let's concentrate on this one particular mirror because it's normal to the high order rotation axis. So this tells us that in the case of para dye substitution, I have the point group D2H. So at this type of substitution, I actually get something different. And let me point out one other thing which is critical about this particular molecule that's useful to us. We also notice that if I make reference to some central point, that no matter which direction I go and draw a vector to a particular atom of the molecule, if I go in the opposite direction and equal distance, I will also come up to the same exact atom. That tells me that I have inside of the point group D2H the operation of inversion. So because we have this inversion, we have a centrosymmetric molecule. And we have a facile, a very easy way to distinguish the ortho and meta diiodobenzene from the para diiodobenzene, because the ortho and meta do not have a center of inversion, whereas the para isomer does. So I can easily distinguish those by using vibrational spectroscopy.